In this video, we are going to discuss one of the most fundamental concepts in the finite element method, the difference between the strong form and the weak form of a beam equation. Understanding this distinction is absolutely essential if you want to truly understand FEM, not just use it as a black box. We'll start from the classical differential equation of a beam, the strong form, and then carefully transform it into the weak form. Along the way, we will see why the weak form is necessary and how integration by parts plays a key role. This topic connects differential equations, mechanics, and numerical methods in a very elegant way. Okay, let's start with the strong form. The strong form simply means the differential equation plus the boundary conditions. So, for a Euler-Bernoulli beam, the governing differential equation is this one as shown here. Here, Wx is the transverse displacement, Eix is the flexural rigidity, and Qx is the distributed load, if we have any. And as you see, Ei is a function of x because it can be different at different points of the beam. For a prismatic beam, Ei would be constant. So now briefly look at the beam element shown here. So when we isolate a small element of the beam of length dx, so we can show the moments and shear. As you can see here, m is the moment, v is the shear, and q is the distributed load. At the right, so these moments and shear become m plus dm and v plus dv. The differential equation of the beam comes directly from enforcing equilibrium of this infinitesimal element. From moment curvature relation, m would be negative Eix d2w over dx2, and from force equilibrium, dv over dx would be negative q, and dm over dx would be v or shear. Combining these relationships leads to the fourth order differential equation we see above. So we have d2 and d2 here. So we are basically dealing with a fourth order differential equation. This is the strong form, a pointwise equilibrium statement. Now let us talk about boundary conditions. For beam equation, we have two types: essential boundary conditions, or EBCs, and natural boundary conditions, or NBCs. So we start first from essential boundary conditions. These are also called geometric, kinematic, or displacement conditions. These boundary conditions are explicitly imposed on the solution. For a beam, the primary unknowns are the displacement Wx and the rotation dWx over dx. So for example, if we have a cantilevered beam like this, we can say that W0 is 0 at x equal to 0, and also the rotation, or dw over dx, at x equal to 0 is 0. We are directly fixing the displacement or rotation at the cantilevered point. So these are the essential boundary conditions because we enforce them directly on the trial solution. However, for natural boundary conditions, the story is different. Natural boundary condition is also called non-essential boundary condition, and these boundary conditions are not directly imposed on the displacement. So instead of displacement and rotation, we have forces such as bending moment, or M, and also the shear force, or V. And you saw in the previous slide that how these forces and moments are related to each other. For example, if we have a moment like this at the end of the boundary, or the other way, like m0, and we have a force like f0, we can say that the moment at x equal to L, if the length of the beam is L, is negative m0, and also the shear force at the end, it should be equal to negative f0. So these present prescribed moment or shear at the end of the beam or at x equal to L. And an important idea, especially for FEM, is that natural boundary conditions are automatically satisfied in the weak formulation. This distinction becomes very important when we derive the weak form. Now let us apply everything to a cantilever beam example. So we consider a beam with length L, flexural rigidity of EI, and with a left boundary which is fixed, and right boundary is subjected to a shear force of F0 and moment of M0. Inside the domain of X, which is between 0 and L, the governing equation is shown here. The right hand side of the equation is 0 because we do not have any distributed load. This is our strong form differential equation in the domain or within the domain. Now look carefully at the boundary conditions. At x equal to 0, since we have a fixed support, so the deformation would be 0 and also the rotation would be 0. These are our essential boundary conditions or EBCs. We directly prescribe displacement and rotation for EBCs. Now at x equal to L, we have a free end with loads. So we prescribe EI d squared omega over dx squared at x equal to L equal to negative m0, and also the shear at x equal to L should be negative f0. These correspond to bending moment and shear forces. These are our natural boundary conditions or NBCs. We are not prescribing displacement. We are prescribing forces here. So in the strong form, we clearly see differential equation in the domain, essential boundary conditions imposed directly, and natural boundary conditions imposed through forces. In the next step, we will see how this structure changes when we move to the weak form. Now we move to the systematic derivation of the weak form. So the step 1 is multiplying the differential equation by weight function. So our differential equation is this one, and we multiply it by tx as a weight function, and then we integrate over the whole domain, which is from 0 to L. So in this case, by applying the weight function and integrating, we are gonna have an integral statement instead of a differential equation. So at this stage, we still have a fourth order derivative acting on W. So d2 here and d2 here. And that is too restrictive for finite element approximation. So we move to the next step. The second step is performing integration by parts or IBP. If you remember, integral of u dv is uv minus v du, and this is the simplest form of integration by parts. So if we apply this formula on the integral statement we have here, so we do that by considering t as our u and the whole thing here as our dv. So after the first integration by parts, we reduce the derivative order acting on w by 1. Now something very important appears, a boundary term. This boundary term is this one, as you can see here. If you notice carefully, this expression involves the shear force. And this is not a coincidence. Natural boundary conditions start appearing automatically through these boundary terms. But we still have third order derivative inside the integral. So d here and d squared here. So we integrate by parts again. And we have the IBP2 here. So now we perform, if we perform the integration by parts for the second time, some other expressions shows up. So the derivative order on w is reduced again. Now we have d squared here, and the highest derivative on w inside the integral is second order actually now. And the boundary terms now contain this one ei d2w over dx2 and d over dx of this expression here, and as you know, this shows the moment and this is the shear. So the natural boundary conditions appear naturally in the formulation. That is why they are called natural boundary conditions. The key insight is that after two integration by parts, the strong form which required C4 smoothness now requires C2 smoothness, and that is very important. So this reduction in smoothness requirement is what makes finite element approximation possible, and this is the heart of the weak formulation. Next, we will simplify this expression and clearly identify the final weak form. The third and last step for finding the weak form is applying the boundary conditions. So, as you know, the essential boundary conditions are applied on W and also dW over dx, which is the rotation. And we know that for the cantilevered beam that we are talking about now, both of them are 0. And we use this t as the weight function for approximation. Since we have these values at x equal to 0, I mean the essential boundary conditions at that point, so we do not need any approximation. And we are not going to use t for approximating w and dw over dx at x equal to 0. So that is why t0 and dt over dx 0 should be equal to 0 at essential boundary conditions. Why? Because we do not need to approximate the essential boundary conditions. And also from the problem that we worked on, we have the values of moment and shear at x equal to L, which are shown here. So if we go back to the weak form that we had here, now we just want to apply this. So something like this: t d over dx ei d squared w over dx squared from 0 to L, and also the same thing for this one. And if you come here, so you see that we are gonna have these terms at x equal to L minus at the same thing at x equal to 0, and again for the second NBC at x equal to L minus the term at x equal to 0. So from the problem that we have, we know that d over dx or shear at x equal to L is f0, and we put it here, actually negative f0. And from the explanation that I mentioned for essential boundary conditions, we do not need to have t at x equal to 0, because we already know that w0 is 0, so this term will cancel out. The same thing for the moment. So the moment at x equal to L would be m0, and we apply it here. And at x equal to 0, there is no need to approximate the rotation. So this term should also be 0, and it will cancel out. So the final weak form, considering these cancellations and the integral we have here, so it would be this value. So this is the integral that we have, and as you can see, from fourth order derivative we reach to second order derivative by integration by parts by twice. So we will have this integral here and also these terms here, and the important thing is that the natural boundary conditions at NB or NBCs at x equal to L are shown up here, and that is very important. So this would be our final weak form, which is an integral equation. So we reached from a differential equation form to an integral equation, and that is the weak form of the beam equation. Now let us summarize everything. On the right we have the strong form. It is written as a differential equation, as you can see. It must be satisfied pointwise in the domain. It requires the solution to be sufficiently smooth up to fourth order derivatives. And the natural boundary conditions are imposed separately. So mathematically, the strong form is very strict. On the left, we have the weak form. After multiplying by a weight function and performing integration by parts twice, we obtain an integral equation as you can see here. Now observe the key differences. It is an integral formulation, not pointwise differential equation. Natural boundary conditions appear automatically inside the equation. The smoothness requirement is relaxed, only second-order derivatives are needed, and this makes approximation methods like Galerkin method possible. So conceptually, the strong form enforces equilibrium at every point. The weak form enforces equilibrium in an average, weighted sense over the domain. And this transition from strong to weak is the mathematical foundation of the finite element method.